forward. So one other thing I want to talk about with beams is something called eigenvalues and eigenvectors. So we're going to look at actually solving y double prime plus lambda y equals 0. Just solving this differential equation. Y of 0 equals 0 and y of L equals 0. So it's a boundary value problem that we want to actually solve and see how this looks. And so we're going to look at the different cases that we can have. They all depend on each one of these pieces. So case 1. Let's just for the moment assume that lambda is 0, which means y double prime equals 0. Taking the integral twice, you're going to get y is equal to c1x plus c2. Y of 0 equals 0. So therefore, c1, c2 equals 0. So we end up with y of L equals 0. So y of L would give me c1 times L equals 0. So that being the case, the only thing that can happen is c1 would have to be 0, because L can't be 0. And so you get y equals 0. Very trivial. Who cares? We don't really want trivial solutions. So we're going to ignore this one. So let's look at case 2. Case 2 is that, let's just look at different things for lambda. Let's say lambda is less than 0. So because it's less than 0, let's let lambda equal negative alpha squared, where alpha is greater than 0, just to make life a little bit easier on us. And so therefore I get y double prime minus alpha squared equals 0. So that would get me that if I solve this, m squared minus alpha squared equals 0. So m is equal to plus or minus alpha. That's why we made it alpha squared. So y would be c1, the cosine or the cosh of alpha x, plus c2, the sinh of alpha x. And we actually did this before we could see this solution. Again, if y of 0 means you'd have c1 equals 0, and y of L means that you'd have c2, the sinh of alpha times L, and that should equal 0. But the sinh is actually never 0. So that means c2 has to equal 0. So again, that means we get y equals 0. Again, trivial solution. Who cares? We don't like trivial solutions. So we're going to look at another situation. Let's get a case 3. So case 3 is going to be that that lambda is positive. And so again, just to make life a little bit easier here, let's let lambda equal alpha squared. We are going to again assume that alpha is positive. That means y double prime plus alpha squared y equals 0. So m squared plus alpha squared equals 0. So m is equal to plus or minus alpha I. So that means now we have y is equal to c1 cosine of alpha x plus c2 sine of alpha x. Again, our boundary conditions are y of 0. Y of 0 would be c1. That would equal 0. Oh, again, c1 equals 0. So that's kind of boring. But now let's look at y of L. Y of L would be c2 sine of alpha L, and that equals 0. Well, that could be 0 if c2 is 0. So c2 could be 0, in which case we're back to y equals 0, and it's boring and who cares. So we're going to ignore this situation. We're going to actually look at the situation where c2 is not 0, because sine can actually be 0. So sine could also be 0. The sine of alpha L could actually be 0. And that could equal 0 when alpha L is equal to n times pi. Remember the sine of 0, sine of pi, sine of 2 pi, sine of all minus pi, any of those pi's will get you 0. So then we have that alpha is equal to n pi over L. This is actually known as, and actually, we're going to go a little bit farther. We're going to tell you that lambda, therefore, is equal to alpha squared. And so lambda is actually equal to n pi over L quantity squared. This depends on the n, so we're actually going to call this alpha n and lambda n. And n can be any number from 1, 2, 3, and onward. These are actually known as eigenvalues. So these are the actual eigenvalues. And so what we're now going to do is, oops, I think I did something wrong. Let me do something real fast. There we go. So I hit the wrong button. Okay. Now we're going to go ahead and look at what those eigenvalues can actually be. So what we mean by eigenvalues is lambda 1, lambda 2, lambda 3, onward and onward. That could be pi squared over L squared, 4 pi squared over L squared, 9 pi squared over L squared, and so forth in this pattern. And this is your sequence of eigenvalues. Then if I look at my function that I was dealing with, I had the sine of alpha 1, the sine of alpha 2, the sine of alpha 3, and so forth. So think of this as the sine, the sequence of sine of pi squared over L squared, the sine, and I'll put that in parentheses, just make sure I've got it there. This x, there's an x there, because it's the sine of x, so there should be an x in all these. Sorry about that. And then, so you can have the sine of 4 pi squared over L squared times x. Then you can have the sine of 9 pi squared over L squared times x, and so forth forever and ever and ever. And this is known as a sequence of eigenfunctions. And this is kind of what we want to work with is getting these ideas of what these are. This gets us into something we call buckling of a vertical column. We're going back to that same modulus that we were working with before. Is equal to minus P times Y, where P again is your load. And what you're going to do is you're going to have some kind of vertical column. So here's my vertical column here. And then what I'm going to do is I'm going to put a load on this. That's what P is my load. Again, I need an axis here. I'm going to call this Y this direction and positive X down this way. This is X equals 0 up here. And we're going to move along here. This is X equals L down here. And we're going to put a P on there. We're going to put a load on there, and this thing's going to buckle a little bit. So the column will actually buckle a little bit. And we get something that looks like this. And so this is kind of what we want to look at, is what's happening with this. Your eigenvalues come into this concept. We can actually go ahead and solve this. And I'm going to go ahead and get this equal to 0. And then I am going to tell you that the top and the bottom aren't going to move. So y of 0 equals 0 and y of L equals 0. So I'm going to solve this boundary conditions. I'm going to go ahead and first off divide through by the EI. So plus P over EI times y equals 0. I can go ahead and solve that. And when I do that, I'm going to get these same ideas. I can go through the exact same thing I just argued about. And my lambdas, my n lambdas are going to be P sub n, or P times n, sorry. P times n, same idea that we just went through, over EI. And so that is what we're looking to find, because that's what lambda sub n is that P times n over EI. And if I were to solve this like we did before, this would be n squared over pi squared, n squared pi squared over L squared. And because it came to us from the idea that y sub n was equal to C2 the sine of n pi x over L. So this is kind of where it comes from. And we have this now, and we can actually see that P sub n, actually was a P sub n, I'm sorry, because it depends on what the load is. So your P sub n is actually equal to n squared pi squared E times I over L squared. The column buckles when the load is one of these values. So this is kind of how we find out what it will be. P sub 1 would be pi squared E I over L squared. This is known as your Euler load. And it's where your first buckling is going to be. So if I have a load of this size that I put on top of this column, it will buckle for the very first time here. The second buckle is because we're dealing with the sine function, you're actually going to have more, you're going to have kind of going in and out and in and out. But this first one is the one that we're looking for. After that, then you'd have other bucklings that can happen, and all of them have to be on this way. And that's just another application of, and this is kind of the introduction to eigenvalues and eigenvectors.